Thank you for giving me a voice. Today, I will talk about solid state oxide fuel cell photolysis. So, what is photolysis? Photolysis is splitting of water by photocatalyst. So some metals, and also as far as then found, also some silicates, but mostly we calling taken from metals, metal oxide, have properties that can absorb some energy, some irradiation, and then transfer into energy. In case of fuel cell, is enough this energy to this semiconducting only metals, because such oxides are semiconducting, conducting, and to split water into hydrogen and gave energy producing. This work is Professor Dr. Wojciechowski from Energy and Fuels Department of Krakow University of Technology, and this is what is there, and he planned to make solid oxide, so not because in different size, with different state. Dr. Wojciechowski wanted to show solid oxide, so semiconductive and math modeling. In this case, what we made, solid oxide fuel cells are important because we have to replace our method of hydrogen production, the other cells, into conventional, not conventional way, and photofuel, photocatalyst, and photolysis, and then producing photo cells, they can make photoelectrolysis, also called, because is making photolysis by using electrolysis, but origin the energy from sun, no from circuit of conventional power plant. So conversion fuel. Important then is to make a proper shape and proper structure, and math modeling helps to make it. High solid fuel cells are most efficient devices to converting chemical energy and electricity as reforms in high temperature range 600 to 1000. These materials are important, for example, in giving energy and water splitter into some plant when high energy requires, for example, in iron. In iron production, which is one of most pollutant and one of most requiring requiring reducing emission, because this is the highest, and steel and glass where it require high energy is suitable, because such solid oxide can work in between temperature 600 and 1000. Doing the project is reforming and induce various fuels production, hydrogen, methane, and some carbohydrates. There is no very high, because you want to do less low, and this we propose solid electrolyte for yttrium stabilized with zirconium oxide. So yttrium is quite rare. So not so very low, but yttrium and zirconia can be used and can work. But in such cases of such industrial steel can be very good because would be little less emission, and such plant would generate less cost for polluting of environment. Their work is functional as a well-functional as an anode, provides a constant supply of reactants to our catalytically active sites, while efficiently draining the products of this reaction. The most anodic material used solid electrolytes, for example, nickel zirconium cyanide, with a porous structure allowing gas to flow. Also good catalyst conductor is nickel. This is other cells. Cathode material is the oxygen reduction is also needed, and for cathode, he proposed lanthanum oxide with perovskite structure, where it contains between one metal, also metal oxide, for example, copper, nickel, iron, cobalt, manganese are most popular, as also as strontium. So these are used, but remember that lanthanum is quite one overvalue, and this is the trouble. But he proposed as well for hypothesis. The companionable high mechanical stresses and their connections. They helps to modify coefficient of thermal extensions due to the fact that high tightness is required from cell to prevent penetration gases between the materials. Cannot create intermediate phases that interfere the cell operation. So we have load, and this fuel is going to supply oxidized ions and penetrate the cathode electrolyte. The cathode is supplied by air, which contains oxygen. Free electrons flowing through the outer circuit from the anode reduce the molecule oxygen of the cathode to the oxygen ions according to the cathode reaction. Here is the reaction product is produced on the anode. Hydrogen oxidation and oxygen reduction take place in triple base boundary, where electrolyte, and gas phase are in contact, and there occurs reaction. Hydrogen plus oxygen gives water and reverse. The splitting is also occurring in triple phase correction, so this place is where place hydrogen is produced. The mathematical model uses MATLAB, propose MATLAB, but also Octave can be as the method for catalyst. There can be introduced Fluent, but Fluent are expensive, and Octave is one of the most because it's free access. So this is the model takes into account to the composition of substrate given into the electron cell operating temperature and the microstructural parameters of electrode and electrolyte. These are amongst the volume fraction of individual substances in active materials, length of triple phase boundary region inside the electrode, active surface on electrode, and tortuosity degree of microstructure complexity. So this is the code calculates current density according to given voltage difference. This helps to set voltage or current voltage characteristic of the entire cell. The ion and electron transport. The ion transport respectively for the anode, electrode anode, and cathode, and is passed between the two conducting phases in triple phase boundary for anode, okay, for cathode, and for anode in double phase boundary that only causes a porous surface material. And these electrons, this gives this ion transport efficiency as as contrary proportional to length and proportional to the porosity. So this is efficiency anode and cathode similar, where effective ion potential and proportional to potential of ionic conductor, and this gives our formulas. And gas diffusion is using Fick equation, and for hydrogen is proportional to potential of anode, and reverse proportional to Faraday's constant. In case of nitrogen is 0 because it's inert gases here, and water vapor is proportional to potential of ionic potential for anode and reverse to Faraday constant. This is the using volumetric is obtained, oxidation is obtained from equation is calculated in grid point throughout the cell, and both contains this solution length of a triple boundary space and area absolute boundary space exchange current density on the anode. This is the formula which contains and is proportional. Then, as used and obtained in measurements by this lanthanide, and obtain the hydrogen production of 60% for vapor and oxidant mixture of 21 oxygen and nitrogen. So fuel was quite well efficiency, and this is the changes of anode. The more triple boundary if was higher, then it was increased higher current density with the lowering with higher voltage. So this is the strength of this phase, and similarly was to anode composition. So it shows that changes microstructure material has also significant effect of performance. For cathode using the type of material belongs to mixed ion and electron conductor group. Thereby, the most important region here is double phase boundary, in which the electrons transported by the outer circuit reduce oxygen from where oxygen ions are directed from the anode. analyze density, and conclusions. Analyzing the current voltage characteristic by increase of working temperature by 100 degrees, increasing the current density by about 2 times. Unfortunately, this way of growing solid oxide fuel cell efficiency is problematic due to the fact of high mechanical stresses occur inside the cell when operating in high temperature. These facts problem of adjusting thermal expansion coefficients for the materials for which the cell is made and the interconnectors used in the fuel cells. And this changing the parameters, we can notice some important regularities. And in conclusion, the results clearly show the feature of parameters of solid fuel cell. And microstructure is some important factor to achieve the stability of design. Thank you very much for listening.